All right. Should be in business. All right. Good. Don't need that. So I got a couple of minutes before we reach the official time, so I can probably say a little bit about the news. There's been a lot of news lately, which is almost always the case in this field. Okay, this one's pretty interesting. Maybe that one, and maybe, yeah, here's a couple that I thought were pretty good. So there's a lot of storm about Saudi Arabia right now because there's journalists got killed, and they have, anyway, turns out New York Times is really on this. Not only did they kill a journalist, and they all to try to silence criticism online, which is, the Russians do it too. And anyway, this is the whole world's doing this. Nobody wants free speech. We don't want it either. Now we're starting to censor the internet. Everybody wants to take the political content they don't want off the internet, but they're pretty ruthless about it. Saudi Arabia, silencing critics. And now it turns out they got an employee inside Twitter to give them access to the account so they could find people's IP addresses to hunt them down. And so Twitter is trying to find the spies inside their agency and kick them out. We all do it. You know, this is what started everyone being mad at Snowden. They revealed how the NSA has got spies and hardware and software in the American companies. They're treating them as adversaries and hacking and spying them to find out things. Yeah.
So Saudi Arabia has spies.
Yes, yes. They have agents inside Twitter. Of course, I'm sure we do too. I'm sure we have spies everywhere. It's why America is the only country I know that has to pretend they're not doing this. Other countries are aware of the fact that they have espionage agencies that are sneaking around everywhere. Americans pretend to be too clean for that, but we're not. We're totally doing it too. Yeah. There is a difference in the consequences. Yes, Saudi Arabia has beheading and stuff. Over here, it is less obvious. Yeah, you're right. But I don't think there's any real difference in the extent of spying. I think there's just a difference in the public opinion about spying. But anyway, it's see this guy here. Trump said the guy's innocent. Well, yeah, Trump. Well, see, and of course, what Trump's doing is he doesn't want to endanger our relationship with Saudi Arabia. So when he said this about Putin, he said it directly, and people got mad. He said, "We let Putin kill people. We kill people too. It's not our problem if he kills people." And that is, I think, what Kissinger called realpolitik. This is probably true, but it's politically unacceptable to say this in America. You have to pretend to be outraged. But anyway, I just got a job offer from Saudi Arabia. I'll let you know what comes of that. Some guy in Saudi. Well, I'm gonna talk to him because he wants to set up like it's a real. I checked into it's a real company in Saudi Arabia. They really do IT and security, and they want to do something like open a branch here, and they want to hire people to do it. And I said, well, I might do it. My students might want to do it. We'll see. Right now, any association with Saudi Arabia will be politically incorrect, but I wouldn't recommend letting that stop anybody. I mean, we are very close allies with Saudi Arabia, which is why Trump is trying to forgive them for whatever they do because we really need them. Like Israel, we'll put up with pretty much anything from them because they're so important to us. Anyway, it's
I used to live there as a kid.
Yeah, did you? Oh yeah. Yeah. Well, what did you think?
Just a whole. I like the total culture shock. You know, run by religious police.
And apparently very restrictive for women, right? Did you find yourself? Yeah.
And then just expats in general had to really watch themselves because they would lock them up or send them, kick them out of the country.
Yeah, yeah. And even the people, it's just like China, the people that leave, that then organize groups to resist the government, they'll hunt you down and silence you or kill you or something. It's just like China. Yeah.
Or if you practice another religion in Saudi.
Oh, yes. Yeah, absolutely. So, I mean, that's why, a lot of purists in America are very upset at our close ties with Israel and Arabia because they both don't really have freedom of religion the way we do and kind of violate our fundamental values. But they're our only partners in an area where everybody hates us. So they're important to us, even though they don't really reflect our values too much. So that's why you have Trump trying to somehow say it's okay and you should just shut up and not. It's a tough thing. Anyway.
I heard and hear that Saudi Arabia had a big military contract and there were other countries bidding for it, including China.
Yeah.
And US got it.
Yeah.
And they don't want to give it up because it means a lot of jobs.
Sure. It's financial, and it's also against terrorism. We have close ties with them for a reason. So yeah, U.S. arms, up in arms over South America, killing one journalist. We ended up killing 50,000. Yeah, absolutely. There's other issues. Anyway, it's I don't want to spend any more time on that because I'm not qualified. But anyway, it's hitting the news. It's quite an issue. And this one I thought is pretty important. So a lot of people are putting stuff on GitHub that exposes their private credentials, like their Amazon Web Access keys. And GitHub is now automatically scanning everything and telling you if something is in there that you shouldn't be in there, which is a pretty good idea. So it'll now warn you if you're doing like the top 10 stupid things on GitHub. That's a really good idea. That'll make it easier for people to know. Anyway, so
Did it get purchased by Microsoft, or is it about
yeah, they just got purchased by Microsoft, and it doesn't seem to make any changes yet, but probably it will. Yeah. Anyway, so we're down to Windows overflows, and then I'll talk about the main Windows hacking project here. So I'll cover these. There I go. Right. So we'll talk about these concepts in Windows, the TEB and the PEB, buffer overflows, address space layout randomization, exception handlers, which we're going to use a lot, and the protections, and some of the Windows 2008 defenses. So in Windows processes, threads are what gets CPU time. Processes are just containers that hold threads, and threads are what actually move forward. So you have a thread environment block, which is the information about this block, and it's partly documented, and effectively it's part of the API, although not really with Microsoft's consent, but it's so important everybody just reverse engineers it and uses it. So this gives you a lot of a lot of information about the process. Like the import address table. And it has an SEH pointer, which we'll talk more about later, but the SEH is the structured exception handler. You can handle exceptions. If there's things like a memory access error or a permission error or divide by zero, if you don't do anything about it in your program, Windows will pop up a generic error box, but that is pretty unprofessional. It's better to write your own handlers in your program to handle these. And if you do, they form the structured exception handler list, which is a list of things that will be called to try to handle the exception. And it will only go to the Windows default handler if you don't handle it. That's called an unhandled exception. But you, as a programmer, you have an opportunity to handle the exceptions yourself, and that's certainly what more professional code will do. So that's what you have a pointer here for that. Here you see pointing to the stack and the limit of the stack. There are segment registers. You will see these if you look in, say, IDA Pro. You have these FS colon and GS colon before things. These were the things that pointed to memory segments, and their FS points to the thread environment block on Windows. They're not used as much as they used to be, but they still show up in disassemblers. And then there's the process environment block, which you aren't supposed to be using directly. You're supposed to be using other API calls that indirectly use it. And Microsoft has not documented it very much. But if you take the malware analysis course, we're doing kernel debugging. It is actually very easy to look at the kernel and see what it's doing. It's not very big. It's not very complicated. So Microsoft cannot really hide anything from you. And a lot of people have done this. All right. So here's what's in the process environment block. It tells you whether the process is being debugged, a flag for that. A pointer to a data structure and all the parameters and a session ID. This is some of the information people have figured out in here. So let's talk about buffer overflows. This is, of course, the classic error we're going to exploit. So now the old technique we talked about on Linux, which is the original Aleph null exploit, is where you overflow the buffer and you overflow all the local variables and you hit the stored return pointer. And then when it returns, you control that address. So that's the standard way to do it, and you typically point to a NOP sled, which it slides down and executes your code. So it looks like this. You have a variable on the stack like name of 20, but you put in more than 20, so you put NOPs and then an egg here. The egg is your reverse shell that you want to execute, and then you pad yourself down to where the return value is, and you put a value in the return value that will point back into your NOP sled. This is why you have to know where the stack is for this to work. That's the classic Aleph null type buffer overflow exploit. Now, there's another way to do it. If you don't have control of the return value by overflowing the buffer, you may be able to hit the SEH and put values in the exception handler that you control. And if that's true, you put a value in there that points to your NOP sled, and then trigger an exception, just perform an illegal instruction of some kind. So that's another way to do it. And that's what this looks like. You overflow, put in your exploit, hit the exception handler, and point back and hit it. Amounts to essentially the same thing, and you still have to know where the stack is, because your data went on the stack, and you have to have an address that points to it. ASLR is the big defense that stopped a whole category of these exploits. Without address-based layout randomization, say Windows XP would just use the first available RAM. So start Windows and use some RAM, start the antivirus and use some RAM, and just use the next available block of RAM for each process. So it was pretty easy to guess where you were. All you had to do was build the server, like the server up there with the same things installed on it, you'd pretty much be able to predict where you are. So with address-based layout randomization, every time you restart the machine, it randomly shuffles all these memory blocks to random physical addresses. All the programs think they're running at virtual address 400,000, but they're in fact all over the place. Those are virtual addresses, and you don't know the actual address of anything, of any of the stacks. So even if you can overrun and hit a pointer, you don't know what to put in there. So, all right. So here are ways to get around this. The most powerful technique, and the one we're going to use in the other project, is return-oriented programming. This is, in fact, very simple. You don't inject code and execute it. You use the code that's already there and execute it. This will defeat most of these defenses. So if you can find an address that you can predict with a jump ESP in it, then you put that address in the return value. It executes a jump ESP, and now it goes to the stack and runs code there. And that is, now you can find the stack and use it without knowing its actual address. This is called trampolining. You bounce off the existing code to get back to the code you injected. Here's the structured exception handler is another way to do it. Windows versions before, I think one of the Windows XP service packs would always put EBX, would always have the address of the structured exception handler so you could find it. And so all you had to do was find pop return and put its address in SEH, because pop would go down the stack and then return. So you would find the SEH handler. It's on the stack anyway. And we'll do this quite a bit in the project. Pop return is a very handy thing. It is fairly common that you want to jump to an address and the address is 2 words down the stack. So this is other ways, and you cannot jump directly to the address. You jump to code that will find the address and go there. This is the beginning of the process of overcoming virtualization, which goes on into virtual machines, and VM-aware malware has the same problem. The malware is running, and it wants to know, am I in a virtual machine or not? And it turns out that virtual machines are not very sneaky. They have really obvious clues that you can easily look to see that you're in a virtual machine. And the same point is here. Even when Microsoft made position-independent executables and started moving them in memory, in fact, a lot of the code still has addresses in it you could use. And that's the problem. It's really a paper-thin defense. All right. And then we've talked about these exception handlers. So if you have some kind of error, it triggers an exception. The code cannot continue executing sequential instructions because they hit an instruction and it can't complete it. And the computer will not proceed to the next instruction anymore because it's very likely that the next instruction requires the previous one to be completed. It cannot continue doing things sequentially. It has to jump to pop up an error message, and that goes to the exception handler. That is, so the exception registration structure is here in the thread exception handler, and it will then call a whole series of these. It will try to handle it with the first handler. If that fails, it'll go to the next handler and the next handler. You can have as many of these as you want, and if they all fail, then it will go to the operating system and pop up a generic error message. So here's an example of exception handler. It's going to be in the exception handler, and down here it's going to cause an exception. And this one just prints up oops, doesn't really do much of anything, but that's the shell of code that you use to write all these exception handlers. In here you have some kind of if statement that decides if this exception is a certain type, then you do something, and if not, you pass on to some other exception handler. You can see it in immunity. With view SEH chain, you'll just see the list of exception handlers. It's just a data structure stored in memory, and it can be overwritten, and we will be overwriting it in some of these Windows projects. You can follow the address to it in the stack. You'll see the exception handler there, pointer to the next SEH record, and so on. So the stack contains a lot of useful pointers that you can use to jump to your malware. So if you overflow the stack, overwrite stored return address. Another issue is you cause collateral damage. We've seen this in the very first project, Tour Project 3. You would overflow the handler in order to jump back and print the winning message, and then the program would crash because you messed up EBP. So you can execute a few instructions after returning, but you can't return from that function anymore or really get too far before it crashes. So this is pretty common, that Stack Overflow makes it possible for you to trigger exceptions. And so here's the game. EBX points to the registration structure. On later Windows versions, after Windows XP Service Pack 1, the registers are zeroed to make this a little more difficult. So here's the old process. You would crash, and EBX points to the registration, so you just have to use jump EBX to get in there. Here's modern Windows processes. The stack of the crash is here, and the third value points to the exception registration structure. It's no longer sitting right in EBX, but you can still get there with pop return. That will still get you to the SEH. And here you see we overflowed the stack. This is letters under our control, 4D, 4D, 4D. That's like a GGGG or something. So this, we were able to overwrite an exception handler. Now we have to get to it, and you can get there with pop return. All right, and so now Microsoft has been trying to stiffen up the structured exception handler. So in Windows 2003, they try to detect if the handler is invalid with a few tests. If the handler points to the stack, it's invalid. You're not allowed to put executable code on the stack and use it in the handler. If it is in a loaded exe or DIL, maybe. If it's marked not allowed, module, that's no good. And if the module has no load configuration directory, then it's all right. So it tries to, in a very general way, prevent you from jumping to things that are obviously not a real exception handler, but it's not too hard to satisfy these conditions and get away with it. So here's other ways to do it. If you use an existing handler, put your code outside all modules, then it will pass this test, or find a module without a load configuration directory, which is a general technique that works on almost all versions of Windows. Windows has many files and many processes, and it almost always is the case that whatever the new defense is, it's not really turned on for every module. Some modules are old and haven't been updated yet, so you can just exploit them using old techniques. All right, and Server 2008 has some new defenses added. Here's a typical SEH attack, where you go to the exception handlers, then you hit some handler, and I'm going to point over here. So this is a normal SEH on the left, going through this, and on the right, I'm going to have an exception and jump to pop return, which will go to code. I'm not quite sure on the details of this, but the point is Microsoft added this safe SEH switch. When you compile code with the safe SEH switch, it will do a much better job of protecting the exception handlers. It will create a whitelist of handler addresses during code compiling, and it won't let you use any other address. This, in retrospect, makes a lot of sense. Why would you let me change the handler to any address? You know at compile time what they are. So if you have new programs after 2003 compiled with this switch, then it will not try to exploit the exception handler. But if you're running old code, this won't save you. SE hop is another one. This is very much like Cisco's process of check heaps. Cisco verifies the heap with a cron job or something every 2 seconds. It walks the whole heap. A heap is a series of chunks of data followed by pointers to the next chunk and the previous chunk. So it starts and hops to the next chunk, gets to the end, and then hops all the way back to make sure the whole chain is valid, because if there was an overflow or a data corruption anywhere on the chain, you would detect it. And Cisco routers do this every 2 seconds, and if the chain is not intact, they throw away everything and reboot the router. Windows machines don't have that luxury because they're not specialized for one purpose where you are willing to accept losing data, but this is similar. So they're going to hop through the handler to make sure that it's intact. And all right, that's what it does. It adds an extra record at the end, walks to the end, and that'll tell you if the next pointers are corrupted. So here's a valid SEH chain. Each code comes back and points to the next one and the next one. And here's an invalid one where someone has attacked it and made it jump to some other process. So it's unable to reach the new record at the end because the chain is broken. So it will detect that. In Server 2008, this stuff is enabled by default in the server versions of Windows, but not the client versions. And you can control it here. So we were able to go to Bowne server, and you control here whether you want to disable it for that one process or not. This is very common that Microsoft gives you the opportunity to override the new protection for individual processes because you might be running an old version of something important like your custom code, and you need to override the protections for that one process. So almost every time Microsoft adds something new, they give you this option. There is some way to have an exception list, because Microsoft is all about backward compatibility, far more than Apple, which doesn't care at all. Many companies are using junk that's 10 years old and they don't care, it's still working. And Microsoft completely supports that. They always have, because they're here to make money. They're here to meet business needs. They're not here to tell a business, you have to buy some other operating system because ours won't remain usable for 10 or 15 years. They try to make sure you can keep using your old stuff as long as you want. They will warn you that it's less safe, but many people don't care. They just want to keep using it. That it's too expensive to rewrite or replace it. So you'll get an error here if the exception can't be handled, and then it will pass that error to the operating system. So that'd be a second chance exception. If it's in a debugger, the first thing that will happen is that it'll go to the normal exception handler, and if it fails, it'll come back to the debugger, so you get a chance to examine it before passing it to the operating system and letting it create an error message. So I got some cahoots. And then I want to walk through probably the most important project in this class, which I'll talk a little more about, exploiting the Bowne server. So let me get my cahoots up. Okay, this is it. All right. All right. Yes, there we go. All right. I think their cello is out of tune in this music. Oh, yeah, yeah. Yeah, they clearly enjoy Halloween. Somebody told me these guys just got a round of funding. They got plenty of money. That's good, because I use it all the time, and it bothers me I'm not paying them any money. I'm too American. Anyway, so, all right. I'll wait a few more seconds. All right, looks like that's it. So, which defense is enabled in servers but not in clients? SE hop, this, by the way, is another thing quite common in Windows. The servers versions of Windows are much more picky than the client versions. If you get a cheap laptop with cheap hardware, you can run a client version of Windows. When you put a server on, it won't accept the drivers. This happens frequently because it's much pickier about servers. Servers are not supposed to just download any old thing and run it. You're really supposed to be able to run relatively professional code. And Microsoft, whereas the clients, people expect to be able to play games and run old junk, and so Microsoft makes it much more open to run dangerous things on a client because the stakes are lower. Anyway. All right, which defense cannot protect legacy code? All right, that's safe set. You have to compile with that switch on. Which one can you enable individually for each process in Windows 7? And I imagine also Windows 10, although I haven't tested it. Okay, that's SE hop. And what's the exploit method? It only worked before Windows XP SP1. That was jumping EBX. And which method defeats ASLR? That's pop return is return-oriented programming, and that is the main way to do it. And we're going to do that in later projects, although not tonight. And which one is a register pointing to the TEV? Okay, that's FS, file segment or something. Anyway, that's a bit of the background here, and now we're going to do some of this stuff. Let me record the winners if I can figure out how to operate my computer. Okay, Caitlin, that's a real name. Ritu might be a real name. Ojai, I don't know. I'll record them that way. And I'm leaving the Zoom going so people can send me a chat message if they wish to give me more information about their name. But right now, I want to talk about this project. A student of mine that was getting the OSCP, Offensive Security Certified Professional, which I highly recommend, the most respected certification for pen testers, said this one project is the most important thing. And this is it, exploiting the vulnerable server on Windows. This is where you go there's a long project. You go through a whole step of finding a vulnerability and exploiting it until you take over a Windows machine. And this is the basic process of taking over machines. So we run this Vuln server software on Windows. Let me bring up my virtual machines. You need a Kali machine, and briefly, and you need a Windows machine, which is the main thing you're going to use. We'll only use Kali at the very end when you're ready to take it over.
Is this something that's actually on?
No, this is a good question. It's not OSCP is not a test. OSCP is a hands-on search. But you won't see this exact product, but this is the process that you have to go through. You'll have a bunch of servers running, and you have to hack into them, and you're not allowed to use Metasploit more than once. You have 36 hours. You have to compromise 4 of 6 servers, and you have to develop 2 new attacks to do it. And this is how you do it. You find a process, and that's what he said. This process is quite useful. I think this also may be even more relevant for the later certification, OSCE, which is exploit development. Another thing people have told me is that this 127 class helped them prepare for SANS reverse engineering certification. So there are various people trying to do this, and I know the Wall of Sheep people that I work with at DEF CON are developing a product for the US military to train them, and it is very much like this class. He's making a product that will have a whole series of services randomly changed to be vulnerable, and let teams of 10 people spend like 2 days hacking into them. And they each see a different custom service, so they have to practice developing exploits from zero. Apparently, there are hundreds of people learning to do that in the US military, enough to pay a contractor to develop a training environment for them like this. So this process is becoming more and more expected. Although I should mention something else that might not be obvious. Attack is only a small part of security. The big part is always defense. That's why I'm really pushing the CCDC competition. We're preparing for it downstairs. That is the most important competition by far, because most of the people are defenders. Most of the jobs are in defenders. Attackers are rare. But there's an ever-increasing number of attackers. A lot of my students are actually getting jobs as pen testers, which a few years ago, it was very rare. It's not that rare anymore. But still, most of the time, you only want defenders.
Yeah, because when I went to the B-side
Yeah.
conference, there was some pen testing companies that
Yes, there are jobs as pen testers,
Yeah.
but it's a small part of the market. Obviously, you need many defenders for every attack.
Don't you know how to attack before you can defend?
Well, that's a very good question. Do you learn to attack first? I teach it that way to keep people interested. Traditionally, they don't. But traditionally, the defenders were useless. So the two do tend to come together. But I just thought I'd mention it in case people really think they're going to learn this attack and get a job in attack. The most natural progression is you learn to attack and then you get a job in defense. That's where most of the jobs are. But knowing how to attack is a good way to get there. But anyway, I just want to make sure I mention that now and then so people don't get a false idea of what you can get out of these classes. Okay, so you got to turn off data execution prevention for the particular attack we're using here because we are going to put code on the stack and execute it. Yeah.
Quick question. The DEP,
Yeah.
is that hidden by Microsoft? I'm having a hard time trying to find it.
No, it's not hidden.
I tried in 2008.
Yeah, it's not hidden directly. But Microsoft has ADD. Every version, they change the name of everything and move the menus around just to torture us. So all the instructions never work. It's very frustrating for people like me that write instructions. They move it all the time. So in Windows 2008, there's still something called a computer, and you can right-click it and go to properties. That's where they used to put this. But in Server 2016, they took it away. You have to open File Explorer and find this PC to get there. They have a whole team of people just to hide everything in each version of Windows. If I was running the company, things would be different.
Yeah, the instructions that time out 2008, they didn't go to computer for properties and put somewhere else.
If you do it on 2016, they took away computer.
Yeah,
They changed the name to PC, and then they hid the entire File Explorer and put it under a special yellow button here. I don't know why they do this. No one understands. The peak of this. No. What Microsoft is like a cult where they have a different religion come in and a guru come in every few years and change all the rules. Like Windows 8 was just madness. They hired a team of experts to figure out if you get a bunch of people who've never seen a computer in their life, what's the most natural thing for them? And they wrote that, completely ignoring the fact that 99% of their customers already have an earlier version. And so they get these weird, and the other thing about it was they wanted to make your computer exactly like your phone. Somebody got this stupid idea, and they spent like 5 years going down this blind alley before they finally admitted, computers are not phones. But they're a very strange company, but they make a pile of money. A lot of people use their stuff, no matter how irritating it is. So I've seen a guy with a t-shirt that said, I get to use a Mac. You have to use a PC. And that's the way it is. Most people have to use these. And so you put up with endless torture to do it. They do change things and move things around all the time. It's very strange. Anyway, so in advanced system settings is where you'll find this stuff here. I think these are performance settings, advanced. Yeah, here's data execution prevention. That's where you can go. And for client versions of Windows, it's set this way. For server versions, it's up here. Everything has DEP unless you add it to the list. For client versions, it turns it on only for the Windows services, and all your programs run without it to make it run more software. And if you're going to make a simple attack like what we're going to do here, you are putting the code on the stack and executing it. And that's what DEP prevents you from doing. When you allocate a memory section, you put permissions on it. You say whether it's executable or not. And the default rule for Windows is write or execute, but not both. So anything you can write to, like the stack, is not executable. So anyway, then you run this Bowne server in Windows. So I've already loaded it here. I'm just going to restart it and then run it. Now remember, when you start something in the debugger, it's not running. It's paused. You see it in the corner. So it's not listening. You can't connect to it yet. You have to hit this button and start it running. So it now says running instead of paused. And now it's listening. And you'll see a window come up here. There. It is now waiting for client connections. And your IP address is here, and it listens on port 9999. So you can test it from any machine, like out here. Let me just use my Mac directly. I can do netcat to that address. And the address is 225.129. And then port 9999. And there it is, vulnerable server. It's listening. And it has various methods. These are, I think, intended to look like an email server. These don't really do anything, but it has a series of commands that have a word, a space, and then some parameters. So you'll find various flaws, mostly for making those parameters too long and overflowing the buffer. And in a later project, you can do some fuzzing to find various vulnerabilities. This product has several vulnerabilities to exploit, but the simplest one is Trun. Trun has a simple buffer overflow, which is what we're going to do here. So you start, let me kill this. I've made a few files here. So we start with fuzzing. Okay, and if here's the address, there's the port, and I can just send A's. So I'm going to send a trun, then a dot, and then a bunch of A's, and I can put in any length I want. So if I run that, Python vs fuzz, and I put in, say, 10 A's, then it says goodbye, it worked fine, it did not crash. If I give it, say, more, like 9,000, then it crashes. Now, if it was outside the debugger, it would have popped up a Windows error message. Since I'm running it in a debugger, it doesn't pop up Windows message. It gives me the more informative message, access violation when executing 41414141. This is the simplest case where I control the EIP. Some of those 9,000 A's went right in the instruction pointer, so this should be pretty easy to exploit. And I could stay at the length of 9,000, but it turns out 3,000 is enough. If I debug, restart, to reload it because it's currently crashed, and now I have to run it again because it always starts paused. Now I can try sending it something else like 3,000. And 3,000 also crashes. Remember, once you choose a length, you want to keep the length always the same, because it is possible that the 9,000 and 3,000 actually crashed on different parts of code. So choose a length and then don't change the length as you try to exploit it, or you'll tend to drive yourself mad as you change the exploit and you're actually changing where the crash is. So after each one of these, I need to restart the server, debug, restart, and run after each time. And if I take a look here, the next thing I need to do, let's get control of the extended instruction pointer. So if I look at this one, vs EIP, whoops, get out of there. I want to, that's right, throw the changes. I want to do vs EIP1 there. All right, so what this does, this just connects to the server on the port down here, and then this is gonna make a non-repeating pattern of characters. So it puts 1,000 A's, and then it's gonna have I go from 0 to 5, and J go from 0 to 9, and K go from 0 to 9, and then just print those out followed by an A. So it's gonna be 000A, 001A, 002A, so it's gonna make 500 4-character groups with a number that keeps changing. So it's just a long, non-repeating series of characters. And in fact, just to make it more obvious, this is going to be the attack. Let me just print out the attack and then stop it. So print, attack, and then exit. So it won't proceed beyond this point. Now when I run that one, that's what it looks like. First it prints 1,000 A's, then it prints this non-repeating stuff. So if 4 of these bytes end up in the EIP, I can find which 4 it is, because every sequence of 4 bytes is unique. That's all this is. So let me get rid of that unnecessary code here. Now it'll send that to the server. And so just run that again. And again, my server crashes. And here's where it crashes, 1A25. Because in ASCII, 31 is 1, 32 is 2, 41 is A. So, and it's right to left. So this is 1A25 are the 4 characters that hit. And that means it is A2, that's 8A25. Here is, I find the 1A25, let's see, 1A is this column. So it's that one. That is the stuff that ended up in EIP. So now I know where to control the EIP. All right. And so it turns out that's what I put in EIP3, I think. No, wait. I'm sending it. I wanted to nano it. Okay. Let me do an LS to see what I have. Okay, vs EIP2. Let's nano that. All right. So I figured out that was 2006 bytes down by just counting my way down. And so then I put the next 4 characters to B, C, D, E. So here's how you build the attack. You have 2006 bytes to get to the EIP, then 4 bytes for the EIP. Then I have padding F, which is enough to make a total length of 3,000, and then I send that. Remember, I always want to keep the length the same to avoid crashing at a different code. So if this is right, it'll put BCDE in the extended instruction pointer. This is very much like what you've done in the projects on Linux. First, you make it crash, then you make sure you understand how to control the EIP precisely. So if I run this one, Python, then it crashes, and you see at the bottom here, let me get rid of this, it says 42, 43, 44, 45, that's BCDE. So now I know where the EIP is. All right, so let's debug, restart, and run again. Now so now I can control the extended instruction pointer. Now, let me go down in my instructions here. We got down to all this nonsense. That's 3,000 A's, and here's the non-repeating pattern. All right. All right, so now we have targeted the EIP precisely, so we have succeeded in controlling it. Now, we need to figure out what to put in there. So, let's take a look and see where ESP points at the point of the crash. The ESP is over here, and this thing is strangely scrolled. Let's just do this to make it visible. Come on, stop messing with me. There we are. That's what I want. There we go. Oh, still won't do it. Oh, there we are. Good. So ESP is here and EBP is there. And let's see what's at the stack. You can right-click this value and follow in dump. You can put anything you want down here. And I'm not seeing what I expected to see there, so let me go back to my instructions. When I had this crash, I wanted to follow ESP, and I expected, oh, I see. I'll see this. I expected to see these Fs. So let me just get back to where I need to be. Debug, restart. Yes. And run. And let's send that attack again and see if I can demonstrate that or not. I do that. Now it hits BCDE. Now if I follow, I hit something changed up here. Follow and dump. There, see, I'm seeing your Fs. Remember what I did? I put in A's, then BCDE, then Fs. So this is part of the code I control, ESP. In fact, if you scroll up just one line, you'll see it's actually a very simple situation. Right after the EIP, it points to the next byte. So I can put my attack right there. And I can easily find it by just doing a jump ESP. And if all I have to do is find a command that jumps to ESP and put that address in the stack, in the EIP. So that's valuable information. Now I know how to design my attack. All right, now the next thing is when I inject code, bad characters are going to break the string, of course, and I'll have trouble. I should mention I was just doing a CTF, and they had code where you could put in zeros, and it took it. You can do that in C. I didn't know that. You can't use strings, but you can use other input routines and accept zeros. However, in this case, the code is using strings, and zeros will break it, which we're going to see. So let's do the bad character test. If I nano the bad characters, okay, all this does is has the same 2006, the same BCDE. Now, where I'm going to put in all those Fs, I'm going to put in 256 characters, all from 0 to 255, and then put in enough of whatever's left to make the total 3,000. So I just have all the numbers. The point is, if one of them terminates the string, I will see that everything after that point does not make it to the server. So this is how you detect if any characters are forbidden. So let's send that one up to the server. Let's see if my server is ready. It is not. So I debug, restart. Yes. And then run. Now my server is listening. So I run that. Okay. Now it crashes, and it crashes with BCDE in the extended instruction pointer, which is what I expect. But what's important is what's in the stack. So I right-click, follow and dump. And now I see the first byte is 0, and after that it's all random junk. So the 0 got in, and everything after the 0 did not get in. This is expected behavior for the C strings library. The 0 terminated the string, so all the rest was ignored. So that's not good, and I have to not use 0. So let's try bad character 2. Oops, I don't want to run it. I want to look at it. Okay, all I do here is start at 1. So I skip 0 and try all the other 255 characters, and again, have enough padding of Fs to make the total length 3,000. So I'm going to send that one. I have to make sure my server is listening. Debug, restart, and then hit the go button. So it's running, not paused. Then I send that in. It crashes at BCDE like it's always going to. And now if I look at the stack, right click, follow in dump, now I see 1, 2, 3, 11, 12, 13, 20, 30, 40, 50, 70. All the data got there, all the way down to FF. So every other character is good. The only bad character is null. That's very handy. Often you find spaces or tabs or carriage returns to be bad, but not in this case. So that means it's going to be pretty easy to make my exploit code. It's pretty easy anyway if you use Metasploit. So now I can, now that I know that none of those characters are bad, I have to find a jump ESP somewhere that I can use it. So the way you do that is you add Mona to Immunity. Immunity is a platform. You can add more code into it in Python, just like you can with Wireshark and Firefox and Chrome. And Mona is a separate download from Corlian, Corlance Coder, the big guy in reverse engineering, did a lot of this stuff. And all you do is download the Python script and then drag it into the right folder where Immunity can find it, which is, the instructions are here. You have to put it in this folder, program files, Immunity, Py commands. And then you can execute these commands in your debugger. And that's what you have down here. So first thing I'm going to do is bang Mona modules. Bang is for some reason, exclamation point is what starts it, and it puts the output in the log data. So what I have here is I have a list of all the modules that are used by this code. And on the right, you see the names of it. Here is something called Bowne server, kernel 32, ntdil, NSIDIL, and so on. So these are the various modules that are running in memory. And here it tells me where they are and what their protections are. Now, you might notice this one here, Bowne server itself, is loaded at the bottom of memory. All the addresses start with 00. So that's not going to do me any good because I can't put addresses like that in my exploit because the null will terminate. So I'm not going to be able to use any addresses in this module. Now here's which protections are turned on, and in particular, the protections I don't want are ASLR and NX. If NX was turned on, then it would not be able to executable. And if ASLR was turned on, it would be jumping all over in memory. And as I said, Microsoft protects the server by turning on ASLR, but they almost always forget to turn it on for everything. So here is something with ASLR turned off and NX turned off. So this particular part of it is still vulnerable to simple old attacks from 20 years ago. And that's all I need. ESS func is loaded in a part of memory that doesn't start with 0, and it doesn't have any modern protection. So if I can find a jump ESP in that module, it will stay where it is, and I can find it and use the program exploit. That's all I have to do. Now, there are various ways to do this. There are even some smarter ways after I learned a little better how to use Mona. But at this time, I just knew how to refer to codes by hexadecimal code, so I had to use Kali to do a disassembly to find out what a jump ESP is. NASM shell is a Ruby script in Kali that will assemble one line of assembly code for you. So you can make a jump ESP and see what it looks like. And it's an FFE4. You could also just look it up online in the Intel assembly manual. But anyway, FFE4 is what I'm looking for. So if you want to find exactly that command, you can search this way. Mona find for this string, FFE4 in the module ESSfunc.dil. That will do it. And so that I think I've got in my up down there. Yeah, there it is. That's the command. If you run that, it finds several occurrences of FFE4 in that module. And all of these will stay put where they belong, so I can use any of these addresses as my EIP. That will cause it to jump this routine, and then it will trampoline off that and run one to the stack, so I can run code I put on the stack even though I don't know where the stack is, which is pretty wonderful. And I can use any of them as long as there's no null in the address. So I just chose the first one. It's as good as anything. And that's what I have here. Now, the next thing is to see if NX is going to hurt me. So what you do is you put up a NOP sled, 16 bytes of null, and then a break. So I'm going to put that where the Fs were, hit the jump ESP. If it works, it will hit the NOP sled, do NOP, 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 and break. If not executable bit is turned on, it will hit the NOP and stop on the NOP saying I can't execute a NOP. That's why it's a very nice test. There is no condition under which you cannot perform a NOP unless an X is turned on. So it's a very simple way to test it. Before I bother generating a payload and fitting it in and all that, this will tell me if I have another problem to solve. So that's VSEIP3. It's here. So this is the dummy exploit I'm using. 16 bytes of NOP followed by a break. If I can run that, then I can also run something else like a Metasploit module. And here is the address that came from Mona, the first one. You can see it there, 6250.11af. This is that address backwards. 6250.11af is the address that will kit a jump ESP. So I just need to restart my server. I'm going to close this log window, debug, restart, and then hit the run button and send this VSEIP up, which is Python VSEIP3. Okay, and now it worked because it hit an int3 command. And if you look here, this, if I scroll up, there's the int3 and there's the NOPS. And if I keep going up, I'm going to hit, there's my injected address, 5011AF, 625011AF. It's trying to disassemble that and interpret it as commands, but it's really just an address. This is the address I injected. It jumped here, it executed, nop, 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 and then it hit the break. So now I'm able to hit the code and the code will run. So all I have to do now is add a real shell there. And that's very easy. And in this project, that's why I think that student thought this one was really important. We also use the right kind of shell, the kind of shell everybody uses, not a listening shell, but a reverse shell. So that's why these techniques are all very important to know. So to make your shell code, you make a reverse shell. Windows interpret a reverse TCP, and you have to tell it the address of your command and control server. This is what almost everybody uses because most people have a firewall on their machine now. So if I start a listening process on port 4444, it won't do me any good because I can't get the SINs into the machine. So what I do is I send an email attachment or something, get people to run code, and they make an outgoing connection. And this is what we've been going through in the CCDC class this morning and all the weeks, learning how to block outgoing connections. A server should not be able to initiate a connection with anybody. You should not be able to open a browser and surf the web on a server. That is unsanitary and dangerous. If you need to get software, you don't open a browser on it. That's why if you may have noticed, if you install a Windows Server, Internet Explorer is in a special security mode and it won't let you download anything. And thus you go into a setting and turn it off. You are not supposed to be surfing the web on a server. That is a terrible, unsanitary thing to do because the web page is full of attacks and exploits. If you want to put code on a server, you're supposed to go to another machine, download it, scan it for viruses, and then move it to the server with a file share or USB stick or something. You're not supposed to be surfing the web on a server for this reason, because the bad guys are sending reverse shells that will phone home from the server. And you don't want them to be able to do that, so your firewall should block all outgoing traffic, which is not the normal condition of a firewall because most people want to be clients. But if you want to be a server, you should not allow your server to be a client. Anyway, so if you're attacking clients, which is mostly what people do, then you want this kind of reverse shell. Let me see what this chat message is. Whoops, I keep hitting the wrong button. All right, is the CCIE test harder? I have not taken either test, but I would think so, yes. Oh, CCIE, oh, certainly. That's another one. CCIE is very hard, very well respected. Beyond the CCIE, CCIE is very, and I don't know if any of this is relevant for CCIE. I would think not. Yes, that's all Cisco stuff. The thing this is relevant for is OSCE and OSCP. Anyway, so this is the command that will make a reverse shell and by the way, while I'm at it, to be more realistic, you shouldn't listen on stupid ports like 4444. You should listen on ports like 80 and 443 that everybody expects traffic to be on. That way your network security monitoring team will not be able to detect the traffic. It just looks like more connections to a web server. And here you have to tell it not to use null bytes. And I want it in Python just because I like to write my exploit code in Python. That's a, yeah. If you listened on port 80, no, because my command and control server will not be serving a real web page. It'll be using this just to control bots. If your command and control server was actually serving web pages, then of course you couldn't use this port.
But what the clue is the user also needs the browser on.
Oh, this is very important. This is the port on the command and control server, not the port on the client. It's the difference between the source and the destination port. So you can connect to one server on port 80, and then you can connect to another server on port 80. You can have a bunch of them open at the same time, and it's fine because your local port is just a high number, like 50,000. It's different for each connection. They come back in by targeting the process on the local ephemeral port. So this is very important, and I didn't understand it when I was new in this business. I humiliated myself because of a bad diagram. So let's take a look at this. If I do netstat minus an pipe more, Okay, notice these established connections. This is my local address, 147, 144, 200, 184. I have one ephemeral port going to this server on 443. I have another ephemeral port going to that server on 443. You can be connected to many servers on the same external port. They're distinguished by this internal port. This entire thing is called a socket. The IP address of the source and the destination, and the port of the source and the destination. And a socket is like your own cable. So the only thing that has to be unique is this entire structure. If I change the local port or the remote port, it's a separate channel and traffic will not get mixed up. So I can run my command and control server out here on 443, and the target can make a client connection to it, and it will not matter that it's also connecting to other things on 443.
So what about on 480?
Same thing. It's just not that common. If I connect to my server on port 80, you can also be connected to other servers on port 80 at the same time, and it won't matter.
So the guy hook up the connection on the other side of 480, but then when they come back,
It transmits and sends with this same number. So if I send from my client up to 443, it sends it back to me down the same socket with a source port of 443 and a destination port of 54525. This is two-way communication. But the thing that's important for us is it was initiated by the client. It was an outgoing connection, which means the original SYN went out. The reason that's important is because the default Windows firewall will not block outgoing traffic, but it will block incoming traffic.
so the foreign address port is 80, and then the sending port is 554 something.
Right, exactly. If you connect to port 80, it would just change this number, but this would still be some random high number. Yeah, and
On the inside, you just differentiate between the 80 traffic and 80.
yes, exactly. On the inside, it just looks at this port number, and every process gets a different port number, a local one. This is the ephemeral port number.
Wouldn't the firewall block your 54 points?
No, because typical firewalls, no, the way the Windows firewall is set, this is a stateful firewall. It allows you to send SYNs out to anyone you want, and then after you do that, it will accept the answer to your question. So it lets traffic in if you asked for it. It's actually time dependent. It's not just doing it by port number. Back in the old days, the early generation first generation firewalls could not do this. They were stupid. They would either have to let a port through or not, and then they'd have that problem. Modern firewalls are context aware, so they look at this state table and see if there's an established connection, and if there is, they let that traffic through. And if there's a packet comes later, after this is timed out, it throws it away. That's very important. Firewalls are smarter than they used to be. Anyway, I'm glad you brought it up because it's easy to get confused, and I used to be confused about that. So I go to my Kali Linux machine, which I'm controlling by SSH here, and it looks like it's working. Okay, and first I need the IP address, which is this number, 225.155, and then I need to make my malware, which is going to be that number, 225 and 155, and that should do it. This will create reverse shell malware that will phone home to my Kali Linux machine on port 443. And by the way, interpreter shells are also encrypted, although they're not encrypted with HTTPS, but they are encrypted. So here's my file. I'll copy that stuff, and that goes into my exploit. So on my Mac, which I'm using as a target platform, I've got VS Shell. And there it is. This is the one I tested before class. I'll just replace it with the new one. Kali gives you different output every time you do this. It has some like random keys to sort of scramble things to make it harder for antivirus to detect, although antivirus will detect these things right away. So this is the full attack. I send 2006 A's. I put that same number in the EIP, so it will do a jump ESP and come back. I left in a 16-byte NOP sled because you need this whenever you use Kali payloads. Metasploit payloads tend to use some extra room. This very much frustrated me until I learned to always give them 16 bytes of NOP sled. Then I put in the stuff I just copied out of MSF Venom, and then I put in enough padding to hit a total length of 3,000, whatever that length is. And there I am, the prefix, the EIP, the NOP sled, the buffer, which is the attack code, and then padding. Then I just send that to the server. So that's Python VS Shell. Now, In order for this to work, I have to restart my server. It's paused, so it's debug, restart, and then run. And I have to have a listener, listen. So I have to set up my Kali machine to be a listener. And that is MSF console. And it's in the project or the commands you need here. There's the listener. Okay, use multi-handler. Here I set the L host to the right address, but you don't really need to bother. You can just listen on all ports, on all IP addresses. So you have to tell it which exploit I'm using, and then set the payload. And I could, here I use, then you see here, I'm required to specify the local host. I don't know why they did this, because I can just set it to 0000. If it was me, I would have just made that the default, because I don't really care. It's a command and control server. It's going to listen on every IP address it has. And now, set L port, 443, and now exploit, which doesn't actually exploit anything. It starts the handler. So now it's waiting for bots to phone home. And if I've done everything right, I can run this, and now my bot phones home. And if you look in here, it's still running. It did not crash. It started another thread and ran threads and launched things. It's running Meterpret inside now. And so now I own that box. I can do get UID and all the usual stuff. I could go, there's get UID, and then there's sysinfo. And then there's help, which shows me all sorts of fun Metasploit things. I can get hashes and all that jazz. In fact, let's see how far I can get. I probably can't do a hash dump. I'm probably not system. Nope. Oh, that's good. Even let me get the hash. I don't have the password hashes. So you can do a lot here. And maybe for good, let's see if we can use Mimikatz. Load Mimikatz. Oh, it let me do that. Well, if that's the case, I can do Kerberos. Oh, yeah. And there we go. I didn't get the password, though, for the local administrator. I expected to. Now, maybe I'm not system. Let's see if I have system. Get system. Let's see, get UID. See, I'm only administrator. That's not powerful enough. Let's get system. And it worked. This is true for old version of Windows. Even modern versions, these Metasploit things usually work. So now that that worked, I should be able to do Kerberos. Nope, still didn't work. I expected to get the administrator password. Maybe there isn't one on this box. I forget.
What is Mimikatz?
Mimikatz is a fantastic attack tool that totally messes with Kerberos and NTLM hashes, and it is extremely powerful. A New Zealand guy, I think Benjamin Delphi makes it. He updates it every few days. Every time Microsoft changes their stuff, he just makes it more powerful. He can totally break through Kerberos, steal the gold. He can do incredible things. It's wonderful. And it's so cool. It's, of course, loaded by default in interpreter shells. When you use that, you can just steal everything out of Windows domains. And Microsoft appears to be helpless. Every time they update it, like within 24 hours, he's updated it to hack in anyway. He's always giving talks at DEF CON with his latest version. He's totally figured out Kerberos, and he's a mile ahead of Microsoft all the time. So anyway, all right. So that is it. That shows you how to take over a Windows machine from start to finish. And those are all several powerful techniques to practice there. So this takes a long time, but it's well worth practicing until you understand how to do these things. All these are important things. So any other questions? All right, well, I guess I'll stop the share and I'll just clean up and go hang out in the lab. Let me see if there's a chat message here. Thanks. Oh, no, good. Glad it helps. Okay, well, I'll stop the share and clean up. All right.